Today we will do some experiments on what Ed Leedskalnin called his perpetual motion holder. Now this is a very simple device. We just take a U-shaped piece of soft iron or mild steel. I got a bar here 10 millimeters in diameter. You can buy up to 12 millimeters at hardware stores, and on each side you wrap a wire coil of about 1,000 to 2,000 turns, and you label the ends red and black for positive and negative inputs, and that makes a north pole here and the south pole here, red and blue, and you arrange it like that. It goes around the bar, and after that, just an electromagnet. After that, we'll add another bar here and see what happens when we put DC power. Now when we do this, each of these little coils makes what's called a longitudinal magnetic field. A coil going around the length of a steel bar makes the magnetic field go that way. So it's wrapping around and the magnetic field goes that way, just as shown. That's the physics. Let's see now what happens. Next, what we have done is to take the red wires from each of these electromagnetic coils of 1,000 turns and connect them to this red wire here and a switch which goes to a DC power supply of 12 volts. We've also taken the black wires from these coils, connected them in parallel to another black wire which is going to be negative, and we'll put them on the same DC power supply with a switch. So when we flip on 12 volts, current will run through that switch. Current will run through each coil, create a magnetic field north-south here like a standard lift electromagnet. We put a bar of soft iron here. It should just snap on and join. Let's just see what happens now. Let's flip the switch, and there the bars jumped on and joined. Now that's quite standard physics. There's nothing unusual. What we're going to do next is what Ed discovered. We'll turn the power down very slowly, and then we're going to flip the switch. Now, in a normal electromagnet, the bar would fall off, but it's still sticking. The bar isn't falling off. Look at that. Now Ed thought this was perpetual motion holding it on. To get this to work, you have to get very good flat surfaces between there and there. It can't be too rough. Okay, won't come off. So let's just take one side off and push it really hard. Okay, now it's come off. Now the question is, will it stick again? Won't stick again. So let's try that with another shape. Okay, now we're going to try it with another shape. The coils are wired up the same way, ready to be flipped on with the DC power supplies, an electromagnet. But instead of this long soft iron bar here, I made another U shape of 12 millimeter mild steel, and we're going to see if it snaps on. Here we go. Look at it snap on. Let's push the ends fit together well. Okay, now let's turn down the power again. Turn off the switch and see what happens. It still sticks. Look at that, it's still sticking. It doesn't have to be a big long flat bar, it can be a big long curved one. And we pull it off. And now after we pull it off and try to stick it on again, very weakly, maybe some attraction, but it won't stick. So what happens if we flip the coils the other way? Now we're doing the same experiment, but we flip the wire coil, so that's north and south, and that's north and south. So instead of the magnetism going around, it's just going down each arm. Let's turn the power on, and it still sticks, as an electromagnet should. But what happens now when we turn the power off? Very slowly. Falls right off. Let's turn the power on again. See, it still sticks like an electromagnet. About 4 amps going through here with the coils north-south, north-south. But unless the magnetism goes around the bar, it won't stick as we turn the power down. Watch, let's flip the switch off. So, we've learned something here, haven't we? Now our next experiment will be to examine whether any electric current is flowing through these two reverse coils through the iron to produce this anomalous effect, or is it just pure magnetism? The best way to do that is just to take some mylar tape insulation, which is very thin, and tape it over the end of one coil like that, so no electric current now can flow that way. We've got a good insulator. So let's put the iron bar here and let's flip on the switch. It still sticks as expected for an electromagnet. Now let's turn off the power slowly and see what happens. Power's going down, switch is off. It still sticks. So even with the mylar there, so no current's flowing around the thing, it still sticks. Therefore we've determined electric current doesn't have anything to do with this, just magnetism. Interesting, isn't it? Let's just repeat this experiment with another shape. Now we've got a long round bar, 12 millimeters, coming to these electromagnets in series, and we put mylar tape over one of them so no current can flow. Now we'll flip the switch and it sticks like an electromagnet. And now we're going to turn the current down slowly, turn the switch off, and it still sticks. Therefore we know that electric current doesn't have anything to do with this. For fun, let's do the mylar tape experiment with this soft iron bar. We go to 24 volts rather than 12, so we can see if strength of the magnetic field has anything to do with it. We're going to flip it on really quickly and it sticks. Now we're going to take the current down slowly, turn off the switch, and of course it sticks. The question is, does it really stick harder than before? Not really much harder than before, so it's not really that voltage dependent. Just for clarity, let's review what we've done so far. If we have an iron bar of a U shape like this, with the magnetic fields in these wire coils north-south, north-south, red to black, and we turn on 12 volts of DC power, a soft iron bar will stick. However, if we turn the power off, the bar will fall off again. So that's interesting, but not what we're studying here. To continue our review, we flip the coils now so it's north-south here, north-south here, so the magnetic field will go in a circle around the iron bar, potentially continue here. Now we're going to flip the current on, and again they stick like an electromagnet. There's no surprises there. But now when we turn the current off slowly, instead of falling off, the bar continues to stick. Now we know there's no electric current because I put mylar tape here, and it still happens. So we're looking at pure magnetism. Typically for a coil wrapped around an iron bar, you get what's called a longitudinal magnetic field. The current goes that way and the field goes that way. So the current's wrapping around the bar and the field's going around like that, south-north, south-north, and here would be a north and here is a south. So what we've done, we've created a circular magnetic field. There's no current. What's happening is we're getting the paramagnetism in the iron. The spin domains are all lining up to become magnetic, and that's what depends on how the coils are aligned. For the coils, a normal electromagnet, we might get spin domains here and here, but doesn't continue through the bar. When we make coils like this, we get a circular magnetic field, and spin alignments continue in a sort of quasi-stable state all the way through the bar. Quasi-stable circular magnetic field of spin alignments, not electric current. And if we release it, show you why it's quasi-stable, now we've lost it. We not only lost it here, but we've lost it through everywhere else, and it won't stick again. So that's exactly what seems to be happening with Ed's device. If we sketch it out diagrammatically, we have one coil here and one coil here, one with a north field, one with a south, one with a south field here, and one with a north. Red and blue, blue and red. And when we add current from this DC supply, then these make longitudinal magnetic fields into the iron through which each coil surrounds, just like it says here. Now, so the spins get aligned under these coils. The spin alignments continue all the way through the iron bar here and here. and also down through this other bar here, which now sticks. We get spin alignments in the iron. Electric current has nothing to do with it. If we put Mylar there or there, it has nothing. So what we're looking at is long-range cooperative spin alignments in the soft iron rather than electric current itself. Nothing's really moving. So in summary, based on these experiments, Ed Leedskalnin's PMH was based on quasi-stable spin alignments in a closed circular longitudinal magnetic field rather than perpetual motion as he suggested way back in 1940. Let's do a few more experiments because there's some interesting things still to study here. Next we're going to do a little experiment where we put on the DC power, but instead of flipping it on or off, we're going to reverse the polarity of the power. So these magnets will go from north-south to south-north alternately every time I flip the switch. So let's just start turning the power on, coming up to 12 volts. And it begins to act like an electromagnet. Now we're going to keep the DC power but keep flipping it. It has no effect. So if we can flip the power in these devices, you can hear the bar moving a little bit, but the bar doesn't come off. So in summary, low frequency AC power still allows this interesting effect to happen, about flipping once per second. Now to conclude, let's do one final experiment. I've got 50 Hertz AC power coming out of this isolation transformer through this little control switch to control voltage, and we're going to put AC power at 50 Hertz through these two coils wired as a normal electromagnet to see what happens. And when we reach a certain voltage, it sticks like an electromagnet. When I turn the voltage off, the bar just falls off. Let's flip the coils and see the other way. Next, we still have AC power, but we're going to turn the power up, but the coils are arranged in an Ed Leedskalnin fashion, north-south, south-north. And we turn on the AC power. You can hear it humming when it comes up. Now I'm going to turn it off again, and we remove the sheet, and the iron bar remains fastened. So Ed's PMH effect, which is really a spin alignment, works either for DC power, very low frequency AC at 1 Hertz, or normal wall AC power at 50 Hertz. Let's take it off now. And there's very little attraction. It won't stick on very long. We've learned quite a lot here, haven't we? Just to conclude, the unusual effects described by Ed Leedskalnin almost 80 years ago, which he called perpetual motion holder, or PMH, are found when we have a bar of soft iron or mild steel bent into a U shape with polished ends and put another iron bar nearby. And when two wire coils are placed on it in series like this, south-north, south-north, rather than the other way around for a standard electromagnet, then the iron gets temporarily magnetized through this iron bar in a circular shape, which remains after the current is turned off, but not after the connection is broken. So there seem to be quasi-stable alignments of the spin in this iron, which are quite long range and not reported elsewhere. My conclusion, therefore, from current studies is that Ed Leedskalnin's PMH was most likely based on quasi-stable spin alignments in a closed circular longitudinal magnetic field. Thank you very much, and hope teachers of physics will educate their students as this important phenomenon, as well as do further classroom demonstrations.